Hey everyone, Mr. Shatter here to take a look at particle motion. We're going to specifically describe the motion of a particle from the context of a problem and from a graph. Let's get started. So here's our first problem. We're going to basically be considering a particle moves along a line at any time t greater than or equal to 0, given by the function s of t equals that quadratic, where s is measured in meters and t is measured in seconds. A. Find the displacement of the particle during the first 2 seconds. Okay. So the displacement of the particle, for A, letter A, the displacement of the particle from 0 to 2 is basically equal to delta S equals F of 2, and we'll use, actually, you know what, we'll use the S just to be consistent. So S of 2 minus S of 0. And so if we use our calculator, we just put it right in here into y equals, and then we can just do vars, y vars function y1 of 2 minus vars function y1 of 0. And this will give us the displacement, which is negative 4. Negative 4 is the displacement for letter A. B. Find the average velocity of the particle during the first 4 seconds. Once you see this word average, you think to yourself slope. I'm not calculating derivatives. So the average velocity is the slope, which is basically y2 minus y1 over x2 minus x1. And we're going to do this for the first 4 seconds. So the questionable values are, we need 0, comma, what, and 4, comma, what. So if I go to my table, just to make this quicker, so it's 0, comma, 3. And 4, comma, 3 as well. So the average velocity, or scooch this down a bit, so the average velocity is equal to y2 minus y1 over x2 minus x1, which is 0. So 0. And let's actually get some units on these. The displacement of the particle during the first 2 seconds is just your position. So it's just negative 4 and will be meters. In the average velocity, now I took a y value and divided by an x value, so now I have a rate, meters per second. Okay, just to be super clear. C, find the instantaneous velocity of the particle at 4. So once it says to find the instantaneous anything, I need a derivative. So I have to find the derivative, so velocity as a function of time is equal to the derivative of position, which is 2t minus 4. And then if I want to plug 4 in, so I want to find the velocity at 4, it's just 2 times 4 minus 4, which is 8 minus 4, which is 4. And since this is a velocity as well, this is a meters per second unit right here, so 4 meters per second. D, find the acceleration of the particle at 4. Well, in order to find the acceleration at 4, I need to find the acceleration function. So the acceleration function is the derivative of velocity. The derivative of velocity is 2. So interestingly enough, even though the question asks me what's the acceleration at 4, the acceleration everywhere is just 2. So the acceleration at 4 is also 2 because it's 2 everywhere. Let's think about a unit here. I took the derivative of velocity, and velocity is measured in meters per second. So the acceleration, which is the derivative of that, is basically adding another unit of time. So it's meters per second squared. Meters per second squared. So 2 meters per second squared specifically everywhere on the function. So just 2. E, describe the motion of the particle. At what values of t does the particle change direction? Okay, well, let's add a new page to answer this question. Add a page. Specifically, let's first answer the question of when does the particle change direction? And a particle changes direction when the velocity changes from positive to negative or negative to positive. Specifically, we want to find out when the velocity is 0, because that's where we're going to change sign there. So if I take my function 2t minus 4 and set it equal to 0, and I add 4, and I divide by 2, I get that there's only one change of sign here of velocity, which is at 2, which makes sense because the original is a quadratic. So I know if quadratics look something like this, that they're going to be, moving one direction, and then they're going to stop, become at rest, and then they're going to move another direction. So one change in sign makes sense. So what's going to happen is I'm going to have the particle doing something from 0 to 2. So 0 to 2, we're going to be doing something. And then the particle is going to stop exactly at 2. So stop. And then from anywhere greater than 2, and I think this experiment goes up to, it doesn't really matter, I guess. It doesn't have a cap, but for any event, all values greater than or equal to 2, the particle is then going to continue. Well, the question is, which way is the particle moving from 0 to 2 and then anything greater than 2? And in order to answer that question, I need to consider the sign of the velocity. If the velocity or the derivative is positive, I know the particle is going right or up. It's depending on the direction of the line. And I know if it's negative, it's moving left or down, of course, decreasing original function. So if I look at the velocity, which is 2t minus 4, and if I plug in a value that's between 0 and 2, I'm going to have a negative value. So the velocity in this interval will be less than 0. That tells us that the particle, whatever this thing is that's moving, is moving, we'll just say right and left for now, so we'll say left is moving to the left, okay? And then the particle is going to stop at t equals 2, since the velocity is equal to 0. And then, from anything greater than 2, if I plug a value bigger than 2 into my derivative, I know my derivative is positive. So if I plug a value greater than 2, I know my derivative is positive. And then I know that specifically my particle is moving right. We'll say right and left instead of up and down. And actually, one quick edit, I think you should be careful, or I should be careful rather, including these or equal to signs here, just because exactly at 2 we're stopping, of course, so we're not really moving right or left. So I'm just going to get rid of those equal signs here. The equal sign on 0 is not a problem, just because it's the start of my example, and I'm going to start moving left right there. So you can get rid of it if you'd like. It doesn't really matter. Exactly at 0, I guess I'm not really moving. I'm just starting out. Anything after 0, I'm going to start moving left. I'm going to stop at 2, and I'm going to start moving right everywhere after 2. So that's what this particle is doing. And you need the derivative, which is basically the slope, in order to answer that question. Okay? Let's take a look at an example from a graph. So this is the graph of a velocity function. So this is velocity on the y-axis here in miles per hour, and on the x-axis we're measuring time. So right here what we have, from this interval to this interval, the velocity is a constant negative 50 miles per hour. So this is a constant speed or rate of change. But interestingly enough, it's a negative velocity, which means this function is moving left. Moving left. Okay? And then what's going to happen is we're now going to be decreasing in speed. Notice my speed here is getting lower and lower and lower as we approach 0. Okay, so we are slowing down. Right there, we're slowing down, decreasing our speed. Right here, our velocity is equal to 0. And that specifically measures a stop. Now, since my velocity function is actually going to change into, we'll change color, into a positive velocity now, I know that at that stop at t equals 5, I know that we had a change in direction. Changes direction. All right? So now, this pink interval, I'm moving to the right. I'm moving to the right, and I'm moving to the right in a positive way. I'm increasing speed. But then from here to here, this interval, I'm still moving right, but I'm moving in a constant 10 miles per hour. I am increasing speed here, increasing, still moving right. Decreasing, still moving right. Right here, I stop. I stop and I change direction. And now I'm going to be moving left at an increasing speed. Increasing speed, still moving left. Here, I'm going a constant rate of change, still moving left. Here I'm going to start decreasing my speed, decreasing my speed, decreasing my speed. Bam. We stop right here. And then we continue on. We're now moving right at an increasing speed, and we are now constant moving right for the end of the problem. Okay? So let's summarize two really important pieces of information. Important piece of information number one. When we move away from the x-axis, okay, we're speeding up. And this is true for our velocity function, okay? So if we're looking at the graph of velocity, we know that when it moves away from the x-axis, the particle is speeding up. And conversely, if we move towards the x-axis, we know our particle is gradually getting closer to zero. The velocity is closer to zero, closer to zero. We know we're slowing down. Okay? Just remember that velocity means slope, and so if this represents our slopes, then that's what the particle is doing. So that would be speeding up and slowing down in the instance of velocity.